Welcome to our video tutorial for question 1 of our daily review. I'm going to remind you that in our video tutorials we're not going to discuss the specific answers to any questions. However, we will be discussing key and important information for how to solve the type of problem that's being asked in this particular question. As always, make sure that you're checking the chapters of the video or the description to find timestamps to get help with any specific one task in this. In question number 1, we're being asked to convert some numbers, and then we're going to determine if those numbers are either rational or irrational numbers. So let's start out by defining the term rational. When we're talking about rational numbers in math, we are describing any numbers that terminate, that means that they end, or that they repeat. They have a repeated pattern when we do those. Let's look at some examples of some rational numbers. 3, -6, 12.5, 1/3, and 1/3 could be turned into a decimal of 0.333, or the square root of 64. Now, we can see in all of these examples that those numbers either end, like 12.5 or 3, or they repeat, like 1/3, which turns into a repeated fraction of 0.333333, and those 3's go on forever. We can determine whether or not numbers are rational or irrational simply by looking at our decimals for those numbers. We can also know that all fractions that can be expressed of 2 integers will give us a rational number. What I mean by that is as long as the numerator and the denominator are positive or negative whole numbers, we will always end up with rational numbers. Let's go ahead and define our term irrational numbers. And irrational numbers are numbers that don't meet those same rules for rational numbers. In other words, they don't terminate or they don't repeat. And everybody in here has probably worked with one irrational number so far in your math experience. And that irrational number that you've worked with so far is the number pi. As many of you know, the number pi is a really special number because it is a decimal number that never finishes. It's infinite. It goes on forever. And as far as we know, we don't have any repeating patterns in that infinite number that is pi. There are also some other irrational numbers, and we're going to be working with those in this problem for problem number 1. Something like the square root of 2 might be a rational number, and you're going to notice that the square root of 2 could be irrational, and we had in the rational column the square root of 64. We'll describe later in this video why the square root of 64 is a rational number and why numbers like the square root of 2 might be irrational. Let's go ahead and just do one final description about our rational and irrational numbers and how these relate to things that you know already. When you started working in math, you probably started with our counting numbers, and this goes back probably to even before you were in school. We learn our counting numbers, which are whole numbers, like 0, 1, 2, 3, 4. Later on in math, we learn about integers. And integers include our counting numbers 0, 1, 2, 3, 4, but they also include negative numbers, or numbers that are on the other side of our 0 in this case, like -3 or -7 or -9. Integers include all counting numbers, and they also include all whole negative numbers. What we're learning about right now are our rational numbers. And we've worked with rational numbers before, but we're just kind of learning that vocabulary if you haven't known it before. Rational numbers include those numbers that kind of fit in between our counting numbers or our integers. Numbers like 1/3, that would be a repeated decimal that we've seen before, 0.33333333. We know that number would go between 0 and 1. That's a rational number. Or a number like 5/7, or even 3.5 or 2.7. All of those numbers fit somewhere in between our counting numbers, or they could fit between our integers as well. We could also have negative rational numbers, like negative 4.7 or negative 2/3. Those would be rational numbers as well. Now, separate from these three circles that kind of connect to each other, we have our irrational numbers, which we are learning about today. And those numbers include things like pi, the square root of 2, and the square root of 30. And we'll talk about our square roots a little bit later in this video. The first task that you're asked to do in problem 1 is to convert. And you might be asked to convert from a fraction to a decimal, or from a decimal to a fraction, or from a decimal to a percent. Here are some of the steps that you can do, and hopefully you already know how to do this. However, if you don't, I'm going to ask you to take a look at a separate video, so click on the link that's here in the description or on this video to find some help about how you can convert between these different forms of our numbers. In this case, it's helpful to be working with fractions and decimals because we know that if our decimal terminates like 0.5, we have a rational number. And we also know that any fraction with an integer of a over b, that will always be rational, and we described that before. So 1 over 2 will always be rational because 1 is an integer and 2 is an integer. Again, if you need some extra help and you need some help with learning the steps to convert our fractions, I would encourage you to go ahead and take a look at the linked video here. Let's talk about perfect squares. Perfect squares are helpful for us identifying rational and irrational numbers. And a perfect square is simply a number that can be expressed as the product of two equal integers. In this case, I've given us an example of the number 25. And 25 is known as a perfect square because we can find 25 by multiplying two equal integers together. This is the product of two equal integers. 5 times 5 will equal 25. That means that 25 meets the requirements for a perfect square. And if you're wondering where that term perfect square comes from, it comes from the fact that we could also write 5 times 5 as 5 squared using an exponent. Now, I would really encourage you to memorize your first 15 to 20 perfect squares. For example, 3 squared. Hopefully we all know that that is 9. Or 6 squared. Hopefully we all know that that's 36. In fact, you probably have the first 10 perfect squares memorized. And if you don't have the first 15 or 20 memorized, I would encourage you to memorize those ones because these perfect squares are really helpful in us determining whether a number might be irrational or rational. Next, let's talk about square roots, which we've heard that word a couple times in our video today. But a square root is the number that when multiplied by itself produces that given quantity. And we've been working with 25, so we'll find the square root of 25, and the square root of 25 is 5, because 5 times itself produces that given quantity of 25. So square roots and perfect squares relate to each other. And again, knowing our perfect squares is helpful because when you're asked to find the square root of 49, for example, you're going to know that that's a perfect square, which will also tell us that that number is rational. And we'll talk about that in just a moment. All perfect squares are going to be rational numbers. Let's do a quick tutorial about how you might use your calculator to find square roots. And for numbers that don't fit in those first 15 to 20 perfect squares, you are more than welcome to use your calculators to help you out. So for example, if you see the square root of 36, you should be able to do that mentally without a calculator because we know that that's a perfect square, like 6 times 6 equals 36. But if you saw a question that asked you to find the square root of 32, if you're racking your brain a little bit, you might be going, man, I don't know any number that I can multiply by itself to get me 32. And that's because it's not a perfect square. So you're more than welcome to use your calculator for this. In this case, I've circled the square root button. And the square root sign, it's the same square root sign that we have. That's actually written in blue above the upward pointing arrow. That's how we would put an exponent on this calculator. Now, if your calculator is different than this, you would simply look for that square root sign and look for how to do that. If you're on a mobile calculator, you may even need to turn your phone sideways so that you can get some more buttons. Sometimes that will give you more buttons. In order to do this, all you have to do on this calculator is push second and then push that exponent button, which will activate the square root, and then we can type in our problem. In this case, the square root of 25 equals 5. That's the example we've been using. Now, let's go ahead and continue talking about our square roots and our perfect squares and how this applies to rational and irrational numbers. We already know that the square root of 25 is 5. We've talked about that a couple times. And we've also talked about the square root of 36 is 6. But if I asked a question like, what's the square root of 30? You're going to notice that we run into a little bit of a challenge. And that is that there's no integer or whole number in between 5 and 6. I can guess about where that number is going to be. However, I certainly don't know what that is off the top of my head. Well, one of the things that I'll tell you is that actually the best way to write the answer for this is going to be the square root of 30. The square root of 30 is simply the square root of 30. That's the most accurate way to write the answer for that. And the reason for that is because the square root of 25 is a rational number. 5 is rational. And the square root of 36 is a rational number. 5 and 6 both terminate or they end. But the square root of 30 is an irrational number. It is going to be a decimal number that does not end and never repeats. In fact, if I go ahead and do that on my calculator now, I'm going to see this decimal number of 5.47722257. And again, you're going to notice that there's no repetition. There's no pattern that's happening in that decimal. And a reminder that actually goes on forever. It doesn't stop there. It simply stops there because that's all that my calculator can display. But it doesn't actually stop there. So we know that the square root of 25 is rational and the square root of 36 is rational, but the square root of 30 is irrational. Now, one final thing to just give you a little bit of caution about. Be careful because obviously all perfect squares are going to be rational. They're going to end up with an integer as our answer. So they must be rational numbers. However, be careful because just because you see a number that's not a perfect square doesn't necessarily mean that the answer to that question is going to be irrational. So let's take a look at one final example. In this case, if I had the square root of 25, if I have the square root of 30.25, I'm going to notice that that is not a perfect square. However, if I think about what I could multiply to get 30.25, and again, you're more than welcome to use your calculators to do this work, we're going to notice that our answer for this is actually 5.5. 5.5 times 5.5 is equal to 30.25, which means that that's a rational number because the 0.5 finished. So be careful. Just because it's not a perfect square doesn't automatically mean that it is not rational. Although it's probably likely, but it doesn't necessarily guarantee that. So just be careful not to make that mistake.